but we'll kind of get started here. Hey everyone, thanks for coming to You're Just Not My Type State. As you can probably tell from the title slide, we'll be talking about Rust a little here and there. Don't worry though, type states are applicable to most languages and frameworks that you're familiar with, and in fact, you've probably written a type state already. If you haven't worked with Rust before, I'll gently introduce the relevant ideas and concepts in it so you can still follow along. Though, as a warning, we'll be showing code samples for Python and Rust, though often in contrast to Python. And we'll also be looking at flow diagrams a bit, so that should help describe some of the ideas in the talk if your Python is a bit rusty. So now that's out of the way, let's get started. So who am I? I've been professional in the security industry since about 2017 and in the broader software industry since 2014. I began working professionally as an Android developer for a relatively large company in Northeast Ohio. After some exposure to security concepts through a Security Week event at a previous employer, I became interested in the field and spent the following years educating myself on security. So I got incredibly lucky somewhere along the way and started my security career as an application security engineer at Dropbox. There, I ran the bug bounty program for a number of years, found vulnerabilities internally, fixed issues, performed security reviews for new products and features, yada yada. These days, I work at Robinhood as a senior security engineer on the application security team. There, I lead the Secure by Construction team, which is responsible for creating paved road solutions to common security problems that arise during the development phase of the SDLC. Anyway, while I was still new to the field, I decided to give bug bounties a try in my free time and quickly became obsessed. After successfully netting around 50 grand from finding vulnerabilities across a variety of different organizations, I started to become a bit disillusioned with the whole idea of bug bounties. While I believe bug bounties are part of a complete SDLC breakfast, I didn't feel like I was meaningfully improving the security of these organizations. One of the depressing things that you come to realize when participating in bug bounties is that the issues you often end up finding are unimaginative and repetitive. It's disheartening that we're still dealing with issues like XSS, despite CSP existing, CSRF, which really should be killed off by now, sorry same-site cookies, and OWASP cheat sheet tier IDORs on big name companies with 300-person plus security teams. While bug bounties are fun, and if you find me after the talk, I'll be more than happy to share some of my favorite hacking stories, I wanted to do something more meaningful with my time than rehash write-ups found elsewhere. You know, the same dish, different flavor style. Another issue I noticed during this time was the tendency for some security teams and organizations to prioritize solving issues that as they arose versus fixing them proactively. Sometimes this trade-off must be made. For example, the relatively recent Log4j CVE was definitely the kind of all-hands-on-deck vulnerability that warranted immediate prioritization. However, not all issues are as bad as Log4j. Is it worth pulling engineers away to mitigate and open a redirect? What about an issue recently rediscovered, but present in your backlog from over 3 years ago? Why the sudden reprioritization? Is this issue actually a big deal? Maybe the lesson you should learn here is that you need to groom your backlog a fair bit more, or even at all. The problem is that without addressing the root of where these vulnerabilities are coming from, we're doomed to the Sisyphean task of interruption, remediation, on-call burden, and a rate of incremental security improvement that hardly registers on an appreciable scale. So, where do our vulnerabilities come from? Well, unfortunately for us, there are a lot of ways that they can occur in the first place. For example, a misconfiguration of services, like this Nginx path traversal that was introduced by forgetting a trailing / in the Nginx config. Or disclosure of secrets, like this jump cloud API key that was leaked on a GitHub repo for Starbucks. Or what about this infrastructure as a service misconfiguration where an EC2 instance was taken down, but not the Route 53 record pointing to it? This allowed a bug hunter to grab the IP address and plant their own EC2 under a subdomain of Uber. Since my background is predominantly application security, the kinds of vulnerabilities we'll be addressing are those introducing at the implementation time by your developers. Misused a library, configured a widget in an illegal way, missing an authorization check on a new endpoint, that kind of stuff. So what might cause developers to introduce these types of security issues? Well, I'd suggest that it's not so much the act of writing code itself that is hard, rather, it's collaboration and code composition. Brian Cantrell, CTO of Oxide Computer Company and the author of dtrace, had this to say on composition. Even if you and I both know how to write memory safe C, it is very hard for us to have an interface boundary where we can agree on who does what. And I agree with this. Have you ever thought, I'm so slow at shipping code at work, and then you crank out a non-trivial side project over a Red Bull fueled weekend? When you control the entire codebase, holding intimate knowledge of its ins and outs and all its various parts, it's easy to reason about and iterate on the design. Additionally, the assumptions and tribal knowledge that may be required to ship the software at your organization are no longer present. You wrote everything. Your only enemy is time in your memory. So how can composition cause problems? Well, let's do an exercise. On the screen is a class definition for a user. It has three methods: log in, do action, and log out. Now, if I asked you to explain to me how this class is supposed to be used, many of you would tell me this. Well, we'd instantiate the class, call login, probably call do action some number of times, and then log out. We wouldn't call log out, then do action, and we probably wouldn't expect to call login multiple times in a row. This is important for us to be aware of. We have no idea if the user is designed to handle some of these atypical interaction patterns. For example, will user stop us from calling do action if our login call failed, or it wasn't even present? What if I called do action after calling log out? Should it fail? Can it succeed if logout failed? Should it succeed? Even though our code sample here is relatively small, we're already presented with questions we'd need to dive into the implementation to answer. Additionally, this whole time we've been mostly assuming that do action requires that we're logged in. That may not be true. On the opposite end of the spectrum of familiarity, we have this code snippet. Here we've defined a foo class with three methods: bar, baz, and thud. How do we use foo now? There's no way to tell. We may need to call bar first, then thud, then baz. Maybe we should never call thud. We'd be guessing without documentation or digging into the implementation. That may have seemed like a ridiculous example, but think about how your developers feel when they look at the documentation for OpenSSL or Python's cryptography library. In these cases, developers rely heavily on documentation to span the gaps in their familiarity and knowledge of the domain. Even then, they often encounter jargon and concepts that they may not be familiar with. If you're lucky, they'll reach out to your security team and get help. If you're not, they may make a critical mistake. This isn't limited to cryptography either. Any code that solves a problem that requires domain knowledge is subject to this problem. If you work at a bank, do you only hire developers that understand complex finance, markets, and concepts? If you build medical software, do your developers understand modern medicine, charting, and in-office procedures? Do you think anyone understands Salesforce? Yet we hire developers to integrate software with it anyway. Believe documentation will solve this problem? Even libraries not specific to fields unfamiliar to your developers can be fraught with assumptions and dangerous behavior, and most of us clearly don't read the documentation for it. Remember the log4j CVE back in December? Digging into the documentation for this library ahead of time should have given pause for concern. Not to mention that everyone knows that the first step to assembling IKEA furniture is to throw away the instructions. In a way, documentation for code is often not that different. Our issues don't just stop with misusing libraries. Composition issues can occur across periods of time where one developer adds on or changes code that another developer wrote previously. The second developer has to build context around the original developer's code to make changes and be careful not to break any expected or unexpected, but depended on, behavior unintentionally. An example of a vulnerability that may have been caused by some composition issues may be CVE 2014-6593, aka skip TLS. Java's JSSE TLS implementation allowed attackers with a man-in-the-middle position to skip steps in the TLS handshake, allowing them to completely compromise the connection. All guarantees typically provided by TLS were given up when the attacker performed this step. They could supply any certificate that they wanted, and the clients would accept them. Another vulnerability similar to skipTLS was the more recently discovered libssh CVE. This vulnerability was an exploit against the shared state machine used in libssh during the initial handshake. Instead of sending the expected SSH user auth request message, the attacker would send the SSH user auth success message. libssh would then pick up from that point in the handshake, allowing the attacker to bypass the authentication portion of the handshake. Thankfully, as we'll see, typestates are actually fantastic at addressing these types of vulnerabilities. So what are typestates? Well, to understand typestates, let's go over what a type is in the first place. At the end of the day, after our code is compiled or JITted down to assembly, your program is not much more than a purposeful set of instructions operating on bits and bytes of memory. And nothing stops us from really programming this way either. You could write x86 or MIPS all you want and build functioning programs this way. But most of us don't. Why? It's much more difficult to make progress this way. It's less intuitive and far more error prone per unit of complexity. Your CPU isn't really considering if a sequence of bytes makes up a sonnet or paints a picture of a sky or corresponds to an email, but people do. We think about what these bits and bytes represent all the time. As a result, we've built languages with type systems. Type systems define the set of rules and logic we wish to apply to our types. And types are just labels we assign to our variables, expressions, and functions in our code that influence the behavior we apply when ultimately validating that our programs are legal. This last step is either done with a compiler, which will throw a compilation error, or shows up at runtime if you're using an interpreted language. We use types to define what are the set of operations that are legal for this particular set of bytes to undertake, and which other collections of bits and bytes are allowed to participate in those operations. For example, in most languages, it's legal to add two integers together, and similarly, it's legal to add two strings. However, in some languages, it's not legal to add the strings and integer together, in others it is. Types allow us to reduce the number of legal programs down to only those that perform operations on our data in a way defined by our type system and, by extension, expected by our developers. So why are types important? Well, aside from stopping programs that almost certainly contain a mistake, they're an awesome feedback loop for developers. If you're using a compiled language like Golang or C#, then your developers can immediately identify programs that will likely do something nonsensical before they reach production. It's much more expensive to fix issues once they've reached production than while the developer is implementing them. Imagine an if statement with a condition that only branches once a year. You do not want to wait a year to get started debugging that behavior in production when it goes wrong. Types allow us to test and validate behavior in these infrequent branches regardless of the condition branching onto them. Speaking of tests, what about them? There's even a development philosophy built around the idea of testing, test-driven development, or TDD. We often use tests to validate the behavior of our programs before we ship them production. This kind of sounds like the next evolution of types, no? Well, not really. Tests can get out of sync with our program as it changes. In many cases, changes in program behavior would need to be accompanied with a new test to ensure that we have full coverage. Sometimes we'll need to update the old tests and update them to our new product requirements. Mocking tests can also be difficult or tedious, especially if your integration tests are depending on I/O behavior. Despite all of this work intending to improve the reliability of our software, our tests may end up being the unreliable ones. How many of you have personally seen flaky tests get in the way of your developers landing code? I know I have. Okay, so back to types. Or back to type states. We've covered type states and types, and we've kind of glossed over some of the reasons why tests aren't necessarily the best, or at least the only way to ensure our program behaves as expected. So, what is a type state? Well, it depends. Type states were originally defined as a refinement on the concept of types. The key differentiation was this. Types define the set of all operations permitted on an object, whereas type states determine which of those operations are permitted in a given context. A common example used when discussing type states is a file type. Imagine we had a file class with an open, close, and read method. We can imagine a scenario where someone tries to call read before they called open file, or where they call read after calling close file. Like the user class example from earlier, we're using a lot of intuition here to determine what the appropriate behavior is. And we're not really forced into a particular pattern, just convention and experience. However, with proper type states, we're actually forced to work with our file type in a particular way. A type state system performs type state analysis on our objects and ensures that they've entered the proper state before we invoke transitions via methods that are unavailable to us otherwise. For example, if we've instantiated a file object but never opened it, we wouldn't even be able to call read in the first place. Likewise, if we call close file, read would similarly result in an error at compile time. That's the original idea behind type states. Unfortunately, as an idea, the language feature hasn't really caught on. Rust actually had this feature back in its early days, but it was removed in 0.4 as it was infrequently used and added unnecessary complexity and long passes to an already slow compiler. So, if type states were removed from Rust, and we haven't really seen them in other mainstream languages, what is the point of this talk? Well, these days, type states have taken on a similar but distinct meaning. These days, type states refer to a design pattern that emulates the benefits of the original type state idea. You've probably already used a type state pattern without even knowing about it. If you've ever used the builder pattern, congrats, you've used a type state. Does this diagram look familiar? It's the process builder and process class from Java. We're required to pass in a proper process name into the process builder constructor before we can call start. We're also able to set the environment variables, the running directory, and many other properties before we call start. If we didn't have a process builder in place, our API would suggest that we could call start, then update the environment variables or the running directory. And obviously to us, the order of operations doesn't make that much sense. However, when we leverage the type state pattern, it doesn't matter if it makes sense to us or not. We're forced to set our environment and running directory before we can call start. We can never update them afterwards. Type states can be constructed in a couple of different ways. One popular way is through distinct types, like we saw with the process and process builder types. Another common method is using generics to track state. For example, we can re-envision Java's process and process builder using generics like so. We define a general process type that takes a generic state that we're calling S, and then we define two more types that we'll use to denote the process state. We can add fields here to record important information about the current state of the process if we want, and we're able to define methods on our process depending on which state we're currently in. This is about as close to type states as we can get. So far, we've mostly looked at examples where type states can be used to solve relatively innocuous bugs, but how can we solve security problems with them? For this first example, we'll look at two classes in Python. The first is a user class, and the second is an authenticated user class. Our goal here is to ensure that developers can only call do action after they've properly logged in. Additionally, if the developer logs out of the account, we do not want to allow them to call do action. So, in simpler terms, we want developers to have to follow this flowchart. We'll start at user always, require a transition to log in, and allow some number of do action calls, then a logout. Unfortunately, this is where Python and other languages tend to break down. There's nothing in the language that is semantically preventing us from calling do action after we've called logout. We can add a check and track the logout call with some internal state. That is not difficult. However, we are assuming we're using a compiled language, we couldn't prove at compile time that we never called do action again. We just kind of have to handle an exception or crash. We can see this problem more clearly if we follow this flowchart that tracks objects created and persisted. Even though we call logout, the logged in user, represented with green, is still hanging around, and in this instance, a compiler is unable to help us transition away from a state. In fact, for most languages, using a type state-based pattern really only lets you benefit on the state transitions into a legal state, but not necessarily away from one. Well, most languages. Remember when we discussed the type systems before? Rust has a very distinct type system from most other languages that you may be familiar with. With most normal languages like Python, Java, C#, and Golang, they use something called normal types. Normal types have that property we saw in the previous flowchart, that once we've created the variable, we are allowed to continue to refer to it even if it's a runtime issue, it is not an illegal program. It's just not a functioning one. Rust, on the other hand, has an affine type system. This means that we're actually able to get the benefit of both moving into and away from legal states when using type states. Rust does this with an operation called move. I won't get into the details much here, as the point of this talk is to primarily focus on the idea of type states, but let's take a quick look at our updated program and flowchart to see what happens when we implement this type state with Rust. Here, our hopefully approachable code sample shows two structs, which are pretty similar to Python classes, defined for both the user and the authenticated user. We define a login method on user that will force a state transition into the authenticated user. On authenticated user, we have two methods defined, doAction and logout. DoAction can be called as many times as desired without forcing a state transition. This is because of that ampersand that's in front of the self there. As logout does not have this ampersand, we're forcing a state transition back into user. Let's take a look at this flow diagram. I've made the nodes that are no longer accessible due to Rust's move semantics translucent. If you attempt to call on those instances afterwards, the compiler would stop you. It's not an exception or panic at runtime. This works so well that we can actually reduce that diagram down into this simple state machine. This is the power of using type states in a language like Rust over other languages. The concept is generally applicable and useful in mitigating some issues on transitions into states. But with Rust, we can reconstruct a full state machine and have a compiler enforce the behavior is correct everywhere. As we can see with our improper usage of the user and authenticated user structs on the left, we encounter a compiler error on the right. This is because the logout call uses a move to terminate the authenticated user object. The compiler knows this and prevents us from interacting with auth user again. Therefore, our doAction call that happens right after becomes a compiler error. While type states help us make our code more approachable and resistant to misuse, I wanted to briefly showcase some cool things you can do with type state design when you take it to the extreme, and maybe inspire some cool ways you can all use type states when you next build software. For that, let's put authorization under a microscope and take a brief look at what type states can allow us to do. Authorization models are infrequently described in sufficient detail to determine which checks and invariants need to be upheld while implementing a new feature or product. It's normal for developers to have to dig through old code and ask veteran coworkers probing questions about features or assets to determine what conditions must be true to avoid introducing an authorization vulnerability. Thankfully, type states can get a strong auth Z, and it won't require tribal knowledge or out-of-date documentation or flaky negative tests. Nor will it require that the caller remembers our arbitrarily complex authorization policy. The details on the design and language features that help us build a compiler-enforced attribute-based access control framework is probably best given in a separate talk or blog post. Here's the high-level summary. We use a distinct type to represent each attribute we're testing, referred to as a test. And we use these types as generics in a nasty nested type called check that we use guard functions that require the relevant test types are present somewhere in this Matryoshka doll of a type. If you feel lost, I don't blame you. What I'm describing doesn't sound ergonomic, it's complicated and likely to result in some implementation mistakes. It's not even obvious what the benefit is in doing all of this. So that's why I created a library called Dacry that does all the hard work for you. It generates all the types from an easy to read and understand policy language with type checking provided by the compiler. Here's an example of what those policies might look like and how Dacry helps us avoid authorization vulnerabilities. Let's use Dacry to start building a bank. We'll define a deposit and withdraw function that requires we perform some tests ahead of time. Deposit will require that the account we're putting money into is not frozen. Withdrawal will require that the account we're pulling money from is not frozen and that the caller is authenticated as that user. Notice that we're able to rely on the previous policy we defined for the deposit function here, so we don't need to rewrite that constraint. Now, when we want to perform our authorization checks, we'll use these constraint functions provided by Dacry. If these are equivalent to the if statements or other control flow you would typically have written to validate your authorization policy requirements. After we perform the tests here using our constraint methods, we're able to call the send money handler. Here's how we define that. Oh, sorry, we did not define that here. If we just to show the what happens if we try to remove one of the constraints, we'll see that our compiler will complain because later on we're trying to call that withdraw function on sender. And because this is a complex type state, our compiler is able to recognize we're not the right type to perform a call to that method. Daiquiri even includes some friendly error messages that tell you exactly what went wrong here. This is really cool. It's our compiler determining, based on the constraint checks we performed, what our authorization rights are at compile time. This makes composition of various policies and entitlements simple. You no longer need to ask your coworker when an account is allowed to do what. Your compiler will tell you. This approach might seem like a lot, but similar ideas are already being used in the wild. In fact, the type state pattern is explicitly used in a ton of software today. Let's take a brief look at a few of them. Anchor is the first example I want to highlight. Anchor is a library used in a large number of Solana smart contracts. It's actually quite similar to Daiquiri in that it elevates some of the authorization tests you'd probably want to perform while writing these contracts into the type system. This makes it easier to audit the source code, as well as identifying object types is easier than hunting for conditionals in the hot path. It makes it a lot easier to develop as well. Anchor uses types like signer, account, program, system, and many others to automatically perform tests during deserialization. This allows strong type-based enforcement of authorization checks. In this example, if the payer account has not signed the transaction, the object cannot be deserialized, causing the transaction to fail entirely. This has huge implications on security. This means that Solana contracts written with Anchor tend to be more safe than those without. Speaking of serialization, Serday, Rust's most popular serialization and deserialization framework. Serday uses methods on the serializer trait to define state transitions into the serialized types. For example, the serialized map method allows us to transition the serializer object into a serializer map object. We can't accidentally serialize a map twice. This is enforced by the type system. This on its own doesn't have much of an effect in security in most cases. However, a popular command line utility that does get security benefits from typestates is curl. Curl is a modular command line utility in that it can support many different backends. Curl currently supports RustLS, which is an implementation of TLS in Rust. As we've seen before, when you use Rust to create typestates, we're able to very accurately describe state machines that the compiler enforces. RustLS uses typestates to build a state machine used in the TLS handshake. This allows for a high degree of confidence that the TLS handshake implementation is one-to-one with specification. Remember skip TLS from earlier? RustLS should not find itself vulnerable to this type of attack. There are many other projects like RT and the Tor project's new client, or Chain's Zero Knowledge Bulletproofs project, intentionally leveraging typestates to enforce security requirements. All right, so that was a lot of things. Here's what I hope that you take away from this talk. 1, the type state pattern is a way for us to determine which actions in a given context are legal, and that this pattern is a useful way to define legal or safe usages of APIs. 2, using this pattern in Rust allows us to ergonomically define a true state machine, which is a useful tool in some contexts, like handshakes. And 3, code composition is a hard problem. Using typestates can help us eliminate assumptions and vulnerabilities that arise during this process. Thanks.